Here's the thing nobody tells you about Brachiosaurus. It didn't die because of an asteroid. It didn't die because a predator finally figured out how to bring it down. It died because of trees. Because over millions of years, it became so perfectly, so completely, so irreversibly built for one specific world, that when that world quietly changed around it, there was nothing left to do but disappear. That is the story we are telling today. The story of the most perfectly engineered land animal in the history of this planet, and how that perfection became the thing that killed it. 155 million years ago, the Rocky Mountains did not exist. Where they stand now, there was a floodplain, vast, flat, subtropical, stretching from what is now New Mexico to southern Canada, without a single ridge to break the horizon. The air was thick and warm and carried the mineral sharpness of wet volcanic ash. Because somewhere to the west, mountain ranges were actively erupting, dusting the river valleys with a fine gray powder that turned the clay a particular shade of gray-blue. The rivers braided and split and reconnected across the floodplain like cracks in old ceramic. In the dry season, the shallow lakes shrank to cracked mud and vanished entirely. In the wet season, they came back as something closer to an inland sea, and rising above all of it, above the fern meadows, above the horsetail thickets, above everything, were the conifers. Araucaria trees, ginkgos, tree ferns, some of them pushing 15 meters into the air, their canopies interlocked into a continuous ceiling of green. They had been growing here, in various forms, for 40 million years. There was no particular reason to think they ever wouldn't. Then the ground shook. Not an earthquake, something slower, something rhythmic. The birds, pterosaurs really, but close enough, went quiet first. Then the ferns at the tree line began to tremble, gently, in a percussion that came from beneath rather than above. And then, from between the trunks, a shape emerged that the human brain is genuinely not wired to process. Not because it was fast, not because it was violent, but because it was so large that the mind keeps refusing to believe the scale, keeps trying to rescale it to something reasonable, and keeps failing. The head appeared first, small, almost comically small, floating at the height of a 5-story building. Then the neck, rising from the shoulders like a structural pillar, 9 meters of muscle and hollow bone and pressurized blood. Then the shoulders themselves, higher than the hips, sloping the body backward like a ramp. Then the rest, the vast barrel of the torso, the thick column legs, each one wider than a man is tall, and finally the tail, extending behind it like a counterweight to the impossible architecture of the front, Brachiosaurus altithorax. It was not the longest animal in this valley. Diplodocus, stretched out with its whiptail, could beat it for length. But length is not mass, and mass is what Brachiosaurus had in a quantity that makes the word large feel like a category error. We will get to the numbers in a moment, but first you need to understand what you are actually looking at, because the thing that makes Brachiosaurus extraordinary is not just the size, it is that the size should have been impossible. And yet here it is, walking through the forest, tearing canopy from 15 meters up, its small eyes blinking slowly in the morning haze, utterly unaware that it is a living solution to a set of engineering problems that should not have solutions. Start with the most basic problem, the heart. The brain of Brachiosaurus sat at the top of a neck that rose roughly 8 to 9 meters above the chest. To push blood upward against gravity across that distance, to keep oxygen flowing to a brain that small at a height that extreme, required blood pressure that would rupture a human cardiovascular system instantly. Biomechanical models estimate the required pressure at around 80 kilopascals, or roughly 600 millimeters of mercury. Your blood pressure right now, if you are healthy, is somewhere around 120 over 80. Call it about 110 millimeters of mercury at peak. In other words, the Brachiosaurus needed a circulatory system running at 5 to 6 times the pressure yours is operating at right now, continuously, for every waking hour of a life that lasted decades. The heart required to generate that pressure has been estimated at around 400 kilograms, 880 pounds. The weight of a grand piano hanging inside the chest cavity, beating without pause, probably aided by a series of one-way valves running up the neck, like a biological check valve system preventing the blood from draining back down every time the head dipped. A 400-kilogram heart beating for decades, keeping a 50-ton body alive. Until one day it stopped, but we are not there yet. Now the weight problem. 56 metric tons for a fully grown adult. That is the upper end of current estimates, and it is a number the human brain processes as an abstraction rather than a reality. So here's the translation. A fully loaded Boeing 757, the kind of aircraft you board at an international airport, weighs around 100 metric tons at takeoff. You are picturing roughly half of that aircraft, on 4 legs, walking across a floodplain. A large bull African elephant weighs 7 tons. You need 12 to 15 of them, standing together, to balance one of these animals. The blue whale is heavier, 100 to 190 tons. But the blue whale is held up by water, by the fundamental physics of buoyancy. Brachiosaurus had nothing, just 4 pillars of bone and muscle, fighting raw gravity, every single step, every single day. And yet the skeleton did not collapse under the weight. Here is why. The vertebrae, the bones of the spine and the neck, were not solid. They were riddled with internal chambers, carved out by a network of air sacs that invaded the bone the way air pockets honeycombs a loaf of bread. Pneumatic foramina, the technical term. The same system structurally as the bones of modern birds. Lightweight architecture that reduces density without sacrificing structural integrity. If you had placed your hand on the neck of a Brachiosaurus and pressed, you would not have felt the dense solidity you expect from something that large. You would have felt something that gave slightly, a hollowness beneath the surface, the faintest suggestion that what you were touching was less like granite and more like reinforced foam. 50 tons of reinforced foam, standing in a Jurassic forest, reaching for the canopy. And there is one more detail about the body of this animal that almost never gets mentioned. Under the broad pads of its feet, particularly the front feet, which bore a disproportionate share of that 50-ton load, the scales were not smooth. They were structured. Small, raised, angular projections distributed across the sole of the foot, functioning mechanically, like the cleats on a soccer boot. In the wet clay of the Morrison floodplain, on the banks of braided rivers where the ground turned to slick mud every wet season, a 50-ton animal without grip would have been a 50-ton disaster. The cleats were the solution. Tiny, almost invisible, doing the quiet work of keeping the largest land animal alive one step at a time. Now here is something almost nobody knows. The skeleton most people associate with Brachiosaurus, the towering, beautifully complete mount that has been photographed millions of times, that appeared in documentaries and textbooks for a century, is not Brachiosaurus. It is at the Natural History Museum in Berlin. It was excavated in Tanzania from a geological formation called Tendaguru, and for most of the 20th century, it was classified as Brachiosaurus branchi, just another species of the same animal. But when paleontologist Michael Taylor conducted a detailed comparative anatomy study, he found over 26 distinct skeletal differences between the African specimen and the actual North American type specimen. The two animals were too different to share a genus. The African animal was reclassified as Giraffatitan branchi, a separate creature entirely, more slender, more elegant, with a shorter trunk, a shorter tail, a more prominent rounded nasal arch. The giraffe of the Jurassic, genuinely beautiful. Brachiosaurus altithorax, the real one, the North American original, was something else. The trunk was 25 to 30% longer. The chest was deeper and wider. The neural spines along the back pointed straight upward, creating a broad, flat ridge, rather than a swept-back fin. The front legs splayed slightly outward at the shoulder, rather than dropping straight down, creating a stance that was wide and planted and immovable. Where Giraffatitan was elegant, Brachiosaurus was a fortress. Where Giraffatitan was a giraffe, Brachiosaurus was a tank that had decided to also be a giraffe. And the real Brachiosaurus altithorax barely exists in the fossil record. The type specimen, the bone assemblage that defines the species, was found by Elmer Riggs in 1900 near Fruita, Colorado. It was a partial skeleton, missing the skull and the entire neck, both of which had been swept away by an ancient river current before the sediment had a chance to preserve them. Based on the unfused joint surfaces of the remaining bones, Riggs determined this was not even a fully grown adult. It was a juvenile, which means the maximum size of this animal is still technically unknown. There is a single humerus, an upper arm bone, found at Potter Creek, now on open display at the Smithsonian in Washington. It is 2.08 meters long. It has been on a touching encouraged exhibit since 1955. Estimates suggest it has been physically touched by somewhere between 200 and 400 million people. That arm bone, one arm bone from one individual of a species we barely have, is the most touched dinosaur fossil in human history. Hundreds of millions of hands, resting on the arm of something that no longer exists. But let us go back to the forest, back to the living animal. Imagine you are standing at the base of a conifer, an araucaria, maybe 12 meters tall, its bark rough and resinous under your hand. The air is humid. It smells of wet fern and something else, something animal and large, a warm smell that has no modern equivalent because no modern animal is large enough to produce it in this concentration. The ground under your feet is damp clay, and it is vibrating, not shaking, vibrating. A low subsonic tremor coming up through the soles of your feet, through your ankles, settling somewhere in the base of your sternum as a pressure rather than a sound. You cannot hear it. You feel it as a kind of atmospheric heaviness, the sense that the air itself has thickened, and then, before you see anything, that pressure deepens. A resonant pulse, like the lowest note an organ can produce, except it is not coming from any instrument. It is coming from a set of lungs the size of a room, forcing air through resonating chambers in a chest that weighs more than your house. This is how Brachiosaurus communicated, not with roars, not with bellowing. Dinosaurs did not have the laryngeal anatomy for mammalian vocalization. Instead, current research suggests they produced closed-mouth vocalizations, the same mechanism used by some modern birds and crocodilians, forcing air through internal resonating chambers without opening the mouth. The result, for an animal this size, would have been infrasound, frequencies below the threshold of human hearing, capable of traveling for kilometers through dense forest, through geological strata, through the bodies of anything in their path. If a herd of Brachiosaurus was moving through this valley, and you were standing in it, you would not hear them coming. You would feel them, a vibration in the sternum, a pressure behind the eyes, the air going strange, and then the trees would start to disappear above you, one canopy section at a time, as something with a reach of 15 meters began its daily work. That daily work was enormous. Brachiosaurus was the exclusive tenant of the top floor of the Morrison food system. The neck and the front heavy body plan gave it access to canopy between roughly 9 and 15 meters, a feeding zone no other animal in the ecosystem could reach. Below 9 meters, the other sauropods competed. Diplodocus at mid-level with its forward projecting neck, Camarasaurus at lower mid, the smaller animals at the base. It was niche partitioning on a vertical axis. Every giant in the same forest eating from a different shelf, which is the only reason a landscape this size, which is basis could support so many massive animals simultaneously, without stripping itself bare. The daily intake required to sustain that 50-ton body has been estimated at 180 to 400 kilograms of vegetation every day. The teeth, 52 spatulate teeth, shaped like wide chisels, slightly serrated, were not designed for grinding. They were designed for raking and stripping. Brachiosaurus did not chew. It tore entire branch loads of conifer needles, tore sections of ginkgo leaf, swallowed everything whole, and left it to a massive hindgut fermentation chamber, a biological vat running somewhere deep in the abdominal cavity, to break down the fiber through microbial digestion over hours. The fermentation produced heat as a byproduct, which helped regulate core temperature. It also produced methane, in quantities that a herd of these animals would have released into the atmosphere at a scale that may have measurably affected Jurassic atmospheric chemistry. A 2023 study by Dr. Michael Demick, mapping body mass evolution across more than 200 sauropod species, confirmed that the brachiosaurid body plan, the front heavy frame, the vertical neck, the massive fermentation-based digestive system, was achieved extremely early in the lineage's history. Not gradually, almost all at once, evolutionarily speaking. The engineering solution appeared, and then it stayed, because it worked. It worked for tens of millions of years, through droughts that emptied the Morrison Lakes, through wet seasons that turned the floodplains into temporary inland seas, through the rise and fall of predators that came and went around it like weather. The predators, by the way, almost never targeted adults. An analysis of nearly 2,400 vertebrate bones from the Mygot Moor Quarry, a Morrison Formation site in Colorado, found that 28.8% of them bore bite marks from large theropods, primarily Allosaurus and Ceratosaurus. 68 of those marked bones came from large sauropods. Critically, not a single one of those bite marks showed evidence of healing. No regrowth, no bone remodeling. The injuries were post-mortem or peri-mortem at the very latest, meaning the theropods were not attacking healthy adults. They were scavenging. They were waiting for the 50-ton fortress to fall on its own terms. Old age, disease, dehydration in the long, dry seasons, and then moving in when the fighting was already over. A stomp from a healthy adult Brachiosaurus, a front leg 2 meters long driving 50 tons into a single point, would have been the mechanical equivalent of an industrial hydraulic press. The predators were not stupid. They waited. But the juveniles were different. Every Brachiosaurus began as an egg roughly the size of a soccer ball. Think about that for a moment. Soccer ball to 50 tons. The same animal. From the moment the shell cracked, the juvenile was alone. No parental protection, no herd shielding. It was immediately small enough, slow enough, and unarmored enough to be exactly what Allosaurus was looking for. The juvenile years were a gauntlet, a race against time, burning calories as fast as the bone microstructure could deposit new material, trying to cross the threshold of size where the calculus changed, where the risk of attacking you became greater than the reward. Most of them never made it. The few that did spent the next several decades growing into something the forest had never seen before and would never see again. For tens of millions of years, this lineage survived everything. The brachiosaurid body plan predated the Morrison ecosystem. It had persisted through environmental upheavals that reset the fauna of entire continents. It had refined itself across geological time into something so specialized, so precisely calibrated, so completely adapted to its specific ecological role, that by the late Jurassic, it had no meaningful competition in its feeding zone, no natural enemy capable of threatening a healthy adult, and no apparent reason to change. By every biological metric, it was built to last indefinitely. The conifers it depended on had been growing here for 40 million years. There was no particular reason to think they ever wouldn't. Sadly, the Jurassic-Cretaceous boundary had no interest in biological merit. It wasn't an asteroid. The asteroid that ended the non-avian dinosaurs was still 80 million years in the future. What came for Brachiosaurus was something slower and in some ways more brutal. The world simply stopped being the world it was built for. At the transition between the Jurassic and Cretaceous periods, the climate shifted. Not catastrophically, not the kind of shift that scorches the sky and blocks the sun, but the reliable monsoon cycles that had maintained the Morrison's enormous conifer forests began to falter. The wet seasons became less predictable. The long droughts became longer, and slowly, generation by generation, the great Araucaria forests, the ones that had been growing in various forms for 40 million years, the ones that represented the entire feeding zone of the most specialized herbivore on the planet, began to thin. New plants were rising to replace them. Flowering plants, angiosperms, better adapted to the drier, more variable climate of the early Cretaceous, lower growing, structurally different, chemically different, and completely useless to an animal whose entire body plan, the towering neck, the front heavy frame, the hindgut calibrated for conifer fiber, had been optimized over tens of millions of years for a resource that was quietly disappearing. The titanosaurs were already waiting. A new lineage of sauropods, more flexible in their diet, built lower to the ground, able to eat from the changing flora. They didn't defeat Brachiosaurus, they simply outlasted it. As the old forest retreated, the titanosaurs expanded. As Brachiosaurus's feeding zone contracted, theirs grew. It was not predation, it was replacement. The slow, silent overriding of one solution by a better adapted one. The last Brachiosaurus altithorax died sometime in the early Cretaceous. We don't know exactly when. There was no witness. There was no last stand. There was just, at some point, a morning in the early Cretaceous when the animal that had solved the impossible engineering problem of being 50 tons on 4 legs, that had built a 400-kilogram heart to defy the physics of blood pressure, that had grown from a soccer ball into the largest land predator's worst nightmare, that had stood in the shadow of its own neck and felt the infrasound of its herd vibrate through the roots of the oldest trees on the continent. There was just a morning when that animal did not wake up, and the conifer canopy it had spent 40 million years learning to reach was already half gone. What we have left is a few scattered bones, one arm that 400 million people have touched, and the fossilized footprints of something so heavy that its steps compressed the clay deep enough to survive 155 million years of geological pressure. But those fragments are enough to reconstruct the whole equation, enough to know that the perfection was real. The engineering was extraordinary. The solution to every physical constraint was genuine and hard-won and built over timescales the human mind cannot hold, and enough to know that perfection in evolution is never permanent. It is always a perfect answer to a specific question. And the moment the question changes, even the most extraordinary answer becomes irrelevant. Brachiosaurus was the greatest land animal this planet ever produced. The world just stopped asking for it. If that ending hit differently than you expected, drop a comment. I want to know the moment this thing stopped being a dinosaur and started being something else to you. And if you know someone who still thinks T-Rex was the most impressive animal in the Mesozoic, send this to them. Let the arm lizard make its case.